Hello. In this video, we're going to be talking about number bases and conversions between number bases. We can write numbers using a base other than 10. If the base is 10, then the possible digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, why is that? Well, that's because we can have 0 groups of 10, or 1, or 2, or 3. But as soon as we get to 10 groups of 10, that actually jumps to the next place value, simply one group of, in this case, 100. Now 100 is the same thing as 10 squared. So essentially, we only have these digits because we can always jump to the next place value. We also can't have 2 digits in one place. And because the base is 10, we can't go beyond 9. So what about if the base is 2? What are the possible digits in this system? Well, we could have 0 groups of 2. We could have 1 group of 2. But as soon as we do 2 groups of 2, that's the same thing as saying 1 group of 2 squared. So the only digits that we have in base 2 are 0 and 1. This is also known as a binary. This is a binary system because there's only 2 numbers, 2 options, 0 and 1 groups. What about if we have base 5? Let's think about this. As soon as we get to the 5 groups of some base 5, all of a sudden it jumps to the next set. So what we can do is we have 0, 1, 2, 3, and 4. Essentially, the number of digits that a base n has is 1 less than the base itself. So in general, if you have base n, then the digits are 0, 1, 2, all the way up to n minus 1. So if we had base 9, we'd have 0, 1, 2, 3, 4, 5, 6, 7, 8. If we had base 3, it's 0, 1, 2. Let's talk about exponential form and other bases. Let's consider the number 24 base 5. This means that we have the number 24 in base 5. Now the base is 5 and not 10, so this is not the number 24. This does not mean 2 10s and 4 1s. This means we have 4 groups of base 5 to the 0 power, and we have 2 groups of base 5 to the 5th power, which is what we have here. We have 2 groups of 5 to the 1st, and we have 4 groups of 5 to the 0. Because this is the first position, or 5 to the 0 position, and then there's this one, which is 5 to the 1st position, which is the same type of system, same type of positioning system as base 10, but instead of 10 being our base, it is now 5. Now let's consider, get rid of that a little bit. Now let's consider 0, 1, 0, 1, 0, or let's try this again. 1, 0, 1, 0, 1, 1, 0, base 2. This means we have the number 1, 0, 1, 0, 1, 1, 0 in base 2. Now the base is 2 instead of 10. And again, the position of the digits gives the place value in base 2, where the farthest one to the right is 2 to the 0, and then 2 to the 1st, 2 to the 2nd, 2 to the 3rd, and so on and so forth. So here's how we get these numbers. This first one comes from there. And we got this first 0 is actually this, and so on and so forth. Essentially, we are taking each place value, which tells me how many groups I have of that base. I multiply that by the value it is. So if we wanted to do exponential form in different bases, we would write it as this. Note that it's not different than base 10 in terms of writing. The difference is simply the fact that we have this base is different. But this base is base 2, and we know that because it's right here. Same thing in the case of the first example. We have base 5, so that means our base for our exponential is 5. And then the values here, the 2 and the 4, represent the number of groups that is in that position, which is no different than in base 10. We just have a different number instead of, the meaning is the same, but the base is a different number. Let's practice converting. So what is 24 base 5 in base 10? Well, we can use exactly what we just did. Based on the positioning system of the number and the base, we know that 24 base 5 is the same thing as 2 times 5 to the first plus 2, or 4, sorry, get a little ahead of myself. Boop. 4 times 5 to the 0. Using the math skills, because now what we've done is we rewrote this expression in terms of base 10. So all we need to do is evaluate the expression. This is 2 times 5, which is 10. 2 times 5. Oh, that's me getting my brain going too fast. 2 times 5 plus 4 times, remember that any base to the 0 power is 1. So we get 10 plus 4, which is 14. 24 base 5 represents the same amount as 14 base 10. Now how can we view that? 2 groups of 5. So we're going to have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then we have 4 groups of 1s. And if we look at the number of circles, we've got 10 circles plus 4 circles. So in base 5, we've got 1, 2 groups, while in base 1 we got 1, 2, 3, 4. Now of course if we were to look at this at base 10, let's use this color for base 10, okay, we have 1 group on base 10 and we have 4 groups of 1, leading us to the number of 14. The point of conversion is not to change the amount of the object we're talking about. It is simply rearranging the number of objects into different size groups. Let's consider 10 in base 10. Now we know that 10 in base 10 is 1 group of 10 and 0 groups of 1. That's literally what 1, 0 means in this case. Let's draw that picture. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in base 10, we have 1 group of 10. But what about base 3? Base 3 is we're going to break it up into different size groups. Let's look at base 3 for a second. We have 3 to the first, or 0 to the 0 is 1. 3 to the first is 3. And 3 squared is 9. Now if I look at 3 to the third, which is 27, is it possible to make a group of 27 from the 10 objects I have? And the answer is no. So we're going to skip that one and say, okay, let's start here. from my 10 objects, can I make a group of 9? And the answer is yes. I can go ahead and say, all right, let's go ahead and count this out. So I have one group of 3 squared. Now, I would look at my next set. Do I have any groups of 3? And the answer is no. So I'm going to have 0 groups of 3 to the first. Finally, we'll do green. I'll do dark blue. Now we have to look at 3 to the 0, which is 1. Here's that. We have one group of 3 to the 0. Now we look at the number of groups from each set. We have 1 group and 0 groups and 1 group. So 10 in base 10 is the same thing as 1, 0, 1, base 3. Again, the number of objects we have is the same. What we're doing is we're arranging the objects into different groups so that way we can express it differently. Now let's do the same thing, but this time in base 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll do the same thing we did before. We have 7 to the 0, which is 1. We have 7 to the first, which is 7. 7 squared, which is 49. Okay, I don't have 49 objects, so I'm going to eliminate that option. We'll look at the next grouping. We have one group. Can we make a group of 7? Yes. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There we go. Okay. This means I have one group of 7 to the first. And then I have 3 groups of 7 to the 0. This means that 10 is the same thing as 1, 3, base 7, where there are 3 singles and then one group of 7. So when we're converting bases, so we converted base 10 into other bases is what we did. Okay, now this is if we have a simple number base, we have a number of 10. We can easily draw and then regroup, but that doesn't always work when you have a larger number. So the question is, which operation are we using? Whoops. So it says, we are regrouping the objects with a different base. What operation is being utilized? You should say division. So now we're going to use division to find the same answer. So we already know that 3 to the 0 is 1. We know 3, 1 is 3, and we know that 3 squared is 9. We also know that we can't go any higher. Since 3 squared is 27, that's too much. I'm going to utilize that one. So I'm going to go ahead and take my 10, and I'm going to divide that by 3 squared. This gives me one group of 9 with a remainder of 1. Now I'm going to take this remainder, and I'm going to take that, and I'm going to divide that by 3 to the first. Now, since I don't have a full group, I'm going to write 0 as my number of groups, and I'm going to have a 1 as a remainder. Now I'm going to take this one, and I'm going to divide it again. But this time I'm going to divide by 3 to the 0. Notice how this is utilizing the stuff we had over here. Now remember that 3 to the 0 is 1, so I have one group of 1 with a remainder of 0. Notice here that the digits lined up here are the digits of our number, where 10 is the same thing as 1, 0, 1, base 3. Same thing with base 7. We have 7 to the 0, 7 to the first. And that's 1. Get that right, Brianne. 1 and 7. Again, we can look at 7 squared, but 7 squared is 49. That's too many objects. So I'm going to take 10 and divide that by 7 to the first. That's going to give me one group of 7. Oops. Let's go ahead and one group of 7 with a remainder of 3. And then we will have, we're going to take that remainder of 3, and I'm going to divide that by the next power, so to speak, 7 to the 0, which gives me 3, remainder 0. Again, the numbers that are here, the number of groups, represents the digits in our number in base 7. So 10 is the same thing as 1, 3, base 7. So when we have larger numbers, we can't necessarily draw the array that we did in the previous slide, but we can always use division. Now your beginnings are there. You know what base you have. So we use that to figure out these numbers, and then we use those to divide. What happens if the base is larger than 10? Let's consider the number 132. What is this on base 12? Well, we have 12 to the 0, which is 1. We have 12 to the first, which is 12. 12 squared, which is 144. Okay, 144 is too high, so we're going to start with 12. 132 divided by 12 to the first. Now, by multiplication, we find that 32 divided by 12 is 11, remainder 0. Now I'm going to take that same remainder. I got to keep the process. I have to go all the way until there's no more numbers I can do. So here, notice that my number of groups is 11 and 0. However, each position can only have one symbol. So we need to figure out what symbol we can use to replace 11, because right now 11 takes 2 spots, but I only can put it in 1. We do so by using letters. So this number is actually, so this will translate to that 132 in base 10 is the same thing as B0 base 12. So the digit's 11, but we cannot use it for one position or place. So instead we use letters, where A corresponds to 10, B corresponds to 11, C corresponds to 12, and so on and so forth. If we end up having more than enough letters, for example, there's 26 letters. Let's suppose that we are in base 32. We could then use lowercase letters to represent the numbers after 26, or whatever number we can go. It is universally recognized that the number 10 is A, B is 11, C is 12, and so on and so forth in bases larger than 10.